So this video would be on descriptive statistics in Maxima. So there is a package called descriptive in Maxima. So the first step would be to load the descriptive package. And it is available by default. One of the functions that this is a utility function, and this has nothing to do with the descriptive package. It is the map function. So map is very similar to apply, and main is a function in descriptive package. So I am going to find the mean of 3 lists. So the first list is going to have the numbers -1, 0, 1.1 and 2, or the second one would have 2, 0, 2, 2, and the third would have 3, -4, 0 and 9. And you can see that I'm putting the 3 lists within a list, so I'm actually creating a list of lists. So what the map function would do is it is going to take the mean function and apply to each of the individual list elements. In other words, it is going to map the mean function to each of the individual elements. And that is the mean. We have 3 individual lists within the list, therefore we end up getting 3 different mean values. So we can also find the mean using or by defining an individual list and simply state mean of S, and that would be 4.1. There is a function called std. Sounds bad, but stands for standard deviation, and the standard deviation is 2.59. There is another function called std1 that is 2.752. So the difference is std is the standard deviation that is based on an unbiased estimator. In other words, the denominator in finding the standard deviation is n. But when we use std1, the denominator is n-1, which is an unbiased estimator for the standard deviation. Now, I could create another list. Let me call it P. And I believe P is of the same length as S, and I could do COV of S, P. I guess I have to define it as a single list. It needs a matrix, so perhaps we could do this later. So what if we had a matrix, just like the apply function in R? We can find the mean of a matrix in terms of columns. So let me just define P as a matrix. And that would be the matrix that we defined. So if we did mean of P, we would end up getting 0, naturally. But what if we have to find the mean across the columns? All we have to do is simply type mean of transpose of P. and that would give us 7 over 2 and negative 7 over 2. Let's see if I can create a data file here. Cannot. So what I'm going to do is I am going to create a CSV file, and you may not be able to see this, but I will post the CSV file. Or I could use an internal data set, so I'll just use an internal data set. So I'll call it W, or let me call it data1, and I'm going to specify read matrix and file search. So that is a data file that is in Maximo. In other words, it comes with an installation of Maximo. So row 1 is a categorical variable, column 1 is a categorical variable with two different levels. One is A, the other is B, and there are 5 different columns, and some of these columns have missing values, and those missing values are denoted by NA. So we can either load data or we can build a sample. Building a sample here is building in terms of a frequency distribution. So we all know what a frequency distribution is. A frequency distribution is one where we have level and we have the corresponding frequencies. So I am going to create a frequency distribution named fruit. And the function to do this is build sample. And I am going to say apple, 19 of them, oranges, 18 of them, grapes, 14 of them. We could have peaches, 12 of them. Now keep in mind, whatever pictures that I'm going to create in Maximo, they're not the prettiest ones, but you know, our goal here is to understand Maximo, so let's just keep on going with this. So if I create this directly, we get an error because we have defined individual lists. But we have to pass a single list of lists, so I'm going to create a list containing 4 different lists, in which case we will not have the error. And if you look at it, it is simply populating 19 apple values, 18 oranges, 14 grapes, and 12 peaches. If you count it, it is going to match up. So our first goal is to create a bar plot or a bar chart. So the basic function in WX Maximo is WX bars plot, and I'm going to use the object that we created, which is fruit, and I'm going to give an X label, which should be the type of fruit, a title, distribution of fruits, And that's what we end up getting. And, you know, as I said, it is not the prettiest graph that one would expect. Now, we can fill in colours for the bars. So I'm going to add another option to the bar graph. So copy and paste. And I did bars colors equals red, and it changed the lines, or the dotted lines that wrap around the bars. But I want the bars filled, so by default the WX bars plot function does not fill. In other words, the density of the color being filled is 0. Now we can change that by specifying another option. And mind you, when we specify the colors, it has to be within square brackets. In other words, it has to be a list. And fill density. So this is going to determine how much we have to fill. So the value of this is between 0 and 1. So I'm going to select 0.2, and I will get fill that is quite transparent. And if I increase it to 0.98, and I'm going to get a full red plot. Just like other commands or plot commands, we could add a Y label. In this case, it's simply the frequency of each fruit. So we have 19 apples, 14 grapes, 18 oranges, and 12 peaches. So the frequency that we see, I believe I forgot to, is the absolute value of the frequency recorded. But what if we want to see the relative frequency? Mind you that relative frequency is simply the frequency divided by the total number of observations that we have. So I'm going to change the Y label to relative frequency, and I could do that by setting another option, frequency equals relative. The default value for frequency is absolute, and that simply means it is going to count the number of apples, number of oranges, grapes and peaches in our example, and the previous particular command simply plotted the absolute frequencies. Here we want to print the relative frequencies. Oh, what did I do? Give me 1 second here. I believe it should be within quotes. Let's try that. zoom this for a second. And there it is. The error was because I split the Y label and put it in two different lines, and clearly Maximo doesn't like that. So we have the relative frequency, and I obtained that by setting frequency equals relative. So the same command, I could change the Y label to percentage and specify frequency as percent. Just like we did relative, here we could save it as percent. And the Y-axis now is in terms of percentages. So there are other things that we can do in terms of options with the bar plot. I'm going to specify box width. I'm going to specify box width to be 2. And it gives me an error. Let's try 0.5. And I got a picture. So it tells us that box width is always a value between 0 and 1. Just like fill density, it was between 0 and 1. So other options for bars plot include ordering, I'm going to specify order less p, and we end up getting that picture. Seems like nothing changed, so I am going to grab the same command and I'm going to replace order less p to order great p, and I end up getting this graph. You should notice the difference between the two. Previously, the bars were in terms of A all the way to Z. It was sorted that way. Here it is just in reverse. It starts with the letter P, which has the greater index in terms of the alphabet, and it goes toward Apple, which is the first alphabet. Now, whatever that we saw earlier is a univariate sample. In other words, I created one single variable, and that happened to be fruits. So I'm going to create a new one. I'll call it fruit and veg. And I am going to build a sample, and it has to be a list of lists. Going to create apple and carrots, and I'm going to put comma 5. then I'm going to have oranges, peas, going to put 4, peaches, beans, going to put 10. And we could see the first column corresponds to the first variable, which is fruit. The second column corresponds to the second variable, which is veg. This is what we call a bivariate sample. We have two variables, fruit and veg. So we want to create a bar graph for this data. And since we have two variables, there is an additional option, which is called grouping, and I'll get to that in a second. Since we have two variables, we need two colors. So I'm going to go for blue and red. Fill density, since we have two colors, I'm going to specify a list. I'm going to use the option grouping equals clustered. It's fruit and veg. Looks like it wouldn't permit a list. So that's what we end up having. So we have the veg coloured in red and the fruits coloured in blue. So that is the clustered version of the graph. And keep in mind, by default, the bars plot is going to graph the frequencies on the y-axis. However, if I change the grouping from clustered to stacked, you can see that it groups the variables together. In other words, it makes an association between first class, the second and the third. So we had a set of apples. Apples were matched to the beans, which is in blue, and carrots with oranges and peaches with peas. So that is the key difference between a stacked plot and a regular clustered plot. Clustered plot simply is going to group the variables, but a stacked plot is going to bring things together and represent it in a different way. And we can also specify ordering here. And we will say order grade P. And that's what we end up having: peas and peaches, oranges and carrots, and apples and beans. So we can actually use a bar graph to visualize continuous and discrete data, but obviously that is not a good choice. We never use bar graphs to visualize continuous data, or discrete for that matter, so I'll show you why. So we could make use of the makeList function. I'm going to, well, since we are dealing with random numbers, let me set a random state. Have to make first. Then set random state. This way, whatever I do will be the same with what you would do when you practice. So I'm going to make list a number between 0 and 20. The iterator is I, and 1 through 15. So that is going to create us a list of 50 numbers between 0 and 20. So that's what we have, or from 0 all the way up to 20. And let me create another list of length 10, of between 0 and 10. But I'm going to add 80 to that. So I have two different samples, two distinct samples, one hovering around 20, the other is hovering around 80. And I could directly plot this using wxBarsPlot. I'm going to specify colors. Put fill density. And that's what we end up getting. And clearly it is not a pretty picture. And mind you, we're actually dealing with discrete values and sort of makes sense or kind of looks alright to us. But what if we had continuous values? This picture is not going to be pretty. What do I mean by that? I am going to create a new list called A. Going to create a random number between or from 0 all the way up to 30, but this time I don't want integers, so I'm going to put 30.0, and I from 1 through 20. That is going to create a list of numbers that are floating point values. And naturally, if I try to do a bars plot on this, this particular graph is not going to be pretty at all. We'll see. I mean, common sense dictates that we shouldn't be using a bar plot to visualize continuous data. I'm just trying to show the concept here. And fill density 0.2 and color. And that's what we get. It is a complete mess because we have only one decimal value. We have decimal values across the real number line, and those are all unique. So the frequency would end up being 1, 1, 1 for every single number. So it's definitely not advised to use this. So what do? We know for continuous data we make use of a histogram. So WX histogram, and let's use the list that we created, A. I am going to use a fill color of blue and fill density 0.8. We can use X label, Y label, and so forth. So X label is data values. And that's what we end up getting. So we have a set of values from 0 all the way up to 20, and clearly there happens to be a break in the middle. We could change the y-axis to reflect a density. All we have to do is change frequency equals density. And those are the density values. Keep in mind, density and frequency are not the same in terms of probability theory. So sometimes we would like to take values and put them in intervals. So it is like creating a frequency distribution. So how do we do this? I'll call it Y. So this would simply mean we are going to create a continuous frequency distribution. So the first step is to make a list, and let's make random values 0 through 20. The iterator is I, and let's generate 50 numbers. And I'm going to put 6 here. So what did it do? It pretty much created classes for us. So the first class is from 0 to 19/6. The next class is from 19/6 to 19/3. The next class is from 19/3 to 19/2. The next one is 19/2 to 38/5. 3, the next one is 38 over 3 to 95 over 6, and the last one is 95 over 6 to 19. And the second element over there would simply be the list containing all the frequencies, and we can verify to see if it adds up to 50, because that is the total number of observations that we have. So sum y of 2, the second list of lists, and the iterator is I, and I is 1 from the length of the second list in the list, and it adds up to 50. So what it tells us is there are 7 elements between 0 and 19 over 6, 10 elements between 19 over 3, 19 over 6 and 19 over 3, 8 elements between 19 over 3 and 19 over 2, and so forth. So, I mean, clearly those are discrete values. Now, what I'm going to do is I'm going to create a continuous frequency distribution with continuous values. Into 6 classes. You should have guessed the answer by now. The answer would be that the frequency is 1 across. So let's see if we get that. We rather got 10, 6, 4, 11, 11 and 8. So what it pretty much did is counted the number of continuous values between 0.213 and 3.493, and it concluded that there are 10 numbers between 0.213 and 3.49. But if I change this, and this is the case where it is going to be 1 across. So discrete freq. In other words, I want to count discrete values and put it into, say, 7 classes. Which didn't work because we don't need the number of classes because those are discrete values. So this is what I was talking about, because each real number is a unique value with frequency 1, so we pretty much end up having number and frequency of 1. But if I used discrete freq and did make list random of 10, I 1 to 20, and it simply concludes that there are 1 1s, 2 2s, 3 3s, 2 4s, 3 5s, and so forth. And there is no 8 in the sample that was generated. So I'm going to go back to the Biomed data that we had. It's data_1. And I'm going to implement something called a subsample. Subsample simply selects a subset of values from the original matrix. So I am going to do subsample data underscore 1. The next argument is something called a predicate function. So it is what's going to do something for us. So what are we going to do? We are going to define a function as a lambda expression. It is going to take in data 1, pass it in, and it is going to give us values for which the first column is equal to A. So if we recall the matrix data underscore 1, it had a bunch of A's and B's in the first column and then a set of numbers. So now I'm asking Maxima to create a subset of data matching the condition that the first column has to be A. So we have selected a subset and every single value here is A. Instead of defining a lambda function, we could also define an expression. What do I mean by that? I could say, I could define a function, say f, the first column has to equal to B, and the second column has to be greater than 36, and the third column has to be less than 20. Those are the conditions that I'm going to impose. So that's what I have. Now I could use subsample on data underscore 1 and use the predicate function that I just defined, which is f. I'm going to call this sub data f. And that's what we get. In other words, there is only one row satisfying that particular condition, and the first value is greater than, or the value in the second column is greater than 39, and the value in the third column is less than 20. So we have seen the column function which would select a specific column from the data. So what I'm going to do is I'm going to create a variable x, and that would select column W or column 3 from W. Not W, it's data underscore 1. And that is the column. And what I'm going to do is I'm going to create a box whisker plot. So box plot x I can specify the width of the box, and it has to be between 0 and 1. So that is the width of the box. I could increase it to 1, and that's what I get. It will span the entire graph. So by default the value is, I believe, 0.75, so I'm going to set it at 0.4, and that's the box we have. And we could change the box orientation to either vertical or horizontal. Right now it is vertical. I could change it to horizontal, and I get the box plot in the horizontal form. So none of the values seem to be outliers, so we don't detect any outliers. But if there were to be outliers, we can use the outlier size command and give it a value 2. As I said, it seems like there aren't any outliers, but if there was an outlier, you should be able to see it here by increasing the size of the outlier. So now we end up having a data set where we have two groups, A and B. And if I have to create a box plot, it is simply going to combine all the values together. But what if each variable, the x-axis and the x variable corresponds to one column, the y variable corresponds to the second column, and so forth? How do we do the box plot? So I'm going to create the wind.data is also an internal data file, so I'll just call it wind, and that is the information we have. So those are the values in that particular matrix, and these are the measurement of winds from 5 different weather stations. If you describe or if you type or Google wind.data in Maxima, you can get more information about it. And I want to do a box plot. So naturally I would say box plot and put wind and give a label, the station ID or station. Y label would be wind. The title, I could specify it as box plot of wind, winds. I think full color is available with box plot also, so let me specify blue, and fill density, it should also be available. That's 0.8. And that's what we end up getting. So that is the regular new plot, but if you want it within WX Maxima, all we have to do is type in WX. And that's what we get. So by the looks of it, it seems like it automatically creates the levels 1, 2, 3, 4 and 5 for the 5 different weather stations. But what if they have names? Then that would be a problem if we used boxplot directly. And what I mean by that is, if we had names for each of these stations, we would want to represent it using those names. So how would we go about doing that? So we make use of the function called wxDraw2D. But within that, we are going to give a description for a box plot. And we are going to create a box plot for the wind data. but I'm going to specify the xtick values. So I'm going to specify the ticks are defined as follows. I'll simply say Miami is tick 1, Fort Myers is tick 2, Tampa is tick 3. I'm making these up. I don't know what weather stations the data corresponds to, but I'm just trying to make a point here. Oops. And you can see that we have rearranged, or not rearranged, we have renamed the default tick values to values corresponding to whatever level that we have. In our case, it is simply the name of the weather stations. So if we have to specify X label, let me just type it over there. I'm going to call it weather station, and I got the X label, and I could do Y label, wind, title, wind distribution, or wind measurements across Florida. And that's what we end up getting. I would expect the box plot to fill, but unfortunately it did not fill. Perhaps I'm doing something wrong, so let me double check here. I guess it doesn't have an option for filling, but you get the idea. As I mentioned at the beginning of the video, Maximo can create pictures, but these days, you know, of course R is much better to create graphics. But if you understand Maximo, things that the way we do things here would relate to R directly. There is some sort of connection, as I've been saying from the very first day of class, that, you know, the languages are related, so whatever we do here will translate to R as well. Not exactly, but very closely.